All right, guys. I hope you all had a good Thanksgiving break, some time off. We are starting chapter 4 today. Chapter 4 is the last chapter we are covering before Christmas break, and it will be the last chapter of this semester. We'll be picking up next semester with chapter 5 and the rest of them. Now, polynomial functions are what chapter 4 is going to be revolving around. A polynomial function is a many-termed expression with monomials, single-term numbers, and variables. Now, these here are 5 different types of polynomial expressions. The first one is a degree 0. If it's a degree 0, we call it a constant function. It's just going to be a number. So negative 14. If it's just a number, it's a constant type polynomial expression with a degree of 0. If the degree is 1, it is going to be linear. It's equation of a line, x to the first. If the degree is 2, quadratics, this is what we covered in chapters 2 and 3, revolved all around quadratic functions, quadratic expressions. And we call it a quadratic because the biggest exponent attached to a variable is 2, so the degree is 2, and it's quadratic. Degree 3 and degree 4. Degree 3 is a cubic, and we know it's a cubic because x to the third is our biggest term, it is cube. X to the fourth is our quartic. Since we have an x to the fourth term, biggest exponent is quartic. And these are all different types of polynomial equations. Questions on this so far? Now, standard form. Writing the polynomial in order of decreasing degree from highest to lowest power. If we have it in that form, it's considered to be in standard form. And the last term is always going to be the constant. If we have a number without a variable, it always goes last. And the number with the variable with the biggest power goes first. And the number in front of the variable or term with the highest power is called the leading coefficient, because every number in front of a variable is called a constant or a coefficient. So in this case, 6 is a coefficient. If it's the first one, if x was the biggest power, 6 would be considered the leading coefficient. Questions on this here? Now, to determine if something is a polynomial function, we could go through and try to list out all the key characteristics that make it a polynomial function. But I think it's sometimes easier just to list some of the features that it is not. So, first thing, exponents aren't negative. If the variable has a negative exponent, it would not be considered a polynomial function. So x to the negative 1 is an example of this here. So x to the negative 1 would not be a polynomial function. Exponents aren't fractions. And especially these first two, we're attaching it to variables. Now we can have 2 to the negative 1 and it'd be a polynomial function. We just can't have x, a variable, to a negative exponent. Same with fractions, fractional exponents. They can be attached to numbers, they just can't be attached to variables. Exponents aren't variables. To the x or y to the x. We cannot have a variable in the exponent at all. It doesn't matter if it's positive or negative. We can't have 2 to the x. We can also not have 2 to the negative x. Variables aren't inside radicals. Does not work. Now, if it's on the outside, that does work. So the square root of 41 times x does work. but just square root of x does not. If the variable is inside the radical, it doesn't work. If it's outside the radical, it does. Variables aren't multiplied together. X times y. We can't have two different variables being multiplied together. Because x squared, x times x is fine. But if we have two different variables being multiplied together, it doesn't work. And variables cannot be in the bottom of a fraction. So if any one of these show up, or more than one of these show up, it is not a polynomial function. Because if it has a variable in the bottom of a fraction, if we have two variables being multiplied together, if a variable is inside of a radical, if we have variables in the exponents, fractional exponents, or negative exponents attached to variables, then it's not a polynomial function. Otherwise, it is. Questions on any of these here? Are you ready for the first one? So let's look at A. So we have a few things we have to do. One, we have to decide whether the function is a polynomial function. If it is, write it in standard form, state its degree, type, and leading coefficient. So if we look at A, negative 2x cubed plus 5x plus 8, is this a polynomial function? Let's go through the list. Are any of the exponents negative? No. Are any of the exponents fractions? No. Exponents that are variables? No. Do we have any exponents inside of radicals? Any exponents in the bottom of a fraction? Any exponents being multiplied together? So, can we say this is a polynomial function? Yes. Okay. Since it is, we need to first write it in standard form. Standard form, the variable with the biggest exponent goes first, and then we go in decreasing order. So the variable with the biggest exponent is negative 2x to the third. X to the third is the biggest one. So after that would be x squared. Do we have an x squared term? No, we don't have to add it in. If it's not there, we don't add it. But x squared would technically go next. Then we'd have x to the first, or just x, which we do have, which is 5x, and our last term is 8. So actually this one was already written in standard form. We just rewrote it back out. Okay, so it is in standard form. Now we want to state the degree. What would the degree of this be? It is 3. The degree is the biggest exponent. Since we are talking about single terms for this whole chapter, we won't have x, y. Because if we had multiple terms, we would add the exponents together to get the degree. Here, it's just the biggest exponent, so it is 3. And if we look back at the chart, if it's a degree 3, it is a cubic. And lastly, we need to find the leading coefficient. So the degree was 3, the type was a cubic, and the leading coefficient is what? Because the leading coefficient is the number in front of the variable with the biggest exponent, which in our case is negative 2. Questions on this here? Let's go to C first. We'll go to B next. So if we look at C, is negative x squared plus 7x to the negative 1 plus 4x a polynomial function? Why not? The negative 1 in the exponent, this is not a polynomial function. It's not a polynomial. It's not a polynomial function because of the x to the negative 1. Incidentally, this would make it a rational, because that is a rational part. Well, we don't have to put it in standard form, say the degree, type, or leading coefficient, because it is not a polynomial function. Let's look at B. Is B a polynomial function? It is. Because we can say for sure there are no fractional exponents or negative exponents or a variable in an exponent. There is no variable in the bottom of a fraction. There are no variables multiplied together. But the one kind of spot, let's see if I can get this to work, that's kind of the big emphasis is that right there. Yes? The square root of 2 times x to the fourth. Is the x to the fourth inside the radical? It is not. The radical stops just right after the 2 because the little bar is not going over the top of x to the fourth. So this is a polynomial function. Now if, get the calligraphy pen back, if it had extended out over x to the fourth, it would technically still be a polynomial function because we can take the square root of x to the fourth. It would just end up being x squared times the square root of 2. But if that variable is stuck inside the radical, then it would not be. But here, it is still outside the radical, so yes, this is a polynomial function. Really, yes, we could put the x to the fourth first. If you notice, sometimes I will put a little down piece, so I'll show you this here. Because the square root of 2 times x to the fourth is the biggest term, it would go first. When I write these out, I'll sometimes put that little drop down to show that it stops there. It doesn't include the x to the fourth. Or if you want to put the x to the fourth in front, that works too. Normally we would do the square root of 2x times x to the fourth, but either way works. Now the next term would be negative 0.8x cubed, because x to the fourth goes first, x to the fourth. Then our x cubed followed by x squared, but we don't have an x squared term, so we won't list it. And it would be x to the first, or just x. We don't have. And the last one's our constant term, which is our minus 12. So we're going 4, 3, 2, 1, technically 0. So that'd be our constant. The degree is 4. Type is, it is a quartic. And the leading coefficient square root of 2. The number in front of the variable with the biggest exponent is the leading coefficient. Because in this here, the negative 0.8 is a coefficient. It's just not the leading coefficient. Last one, letter D. Is this a polynomial function? No, we have 3 to the x. Okay. The leading coefficient is just the number in front of the variable with the biggest exponent. Because the coefficient, leading coefficient, coefficients are just numbers. Questions on these here? Do we need to see another example of one of these? Because if we feel comfortable with these, we'll keep moving forward. Because 1 is yes, 2 is no, 3 is yes. Number 1, the degree would be 2. It would be a quadratic, and the leading coefficient would be negative 1.6. Number 3, the degree would be 4. It is a quartic, and the leading coefficient is positive 3. All right. The next thing we're looking at is evaluating these polynomial functions. So we want to evaluate f of x equals 2x to the fourth minus 8x squared plus 5x minus 7 when x is 3. Well, all that means, put 3 in the place of x. So we have 2 times 3 to the fourth minus 8 times 3 squared plus 5 times 3 minus 7. At this point here, we could type that whole thing into the calculator. Because if we type the whole thing in, we'll get the answer. If we wanted to do this by hand and simplify it, 3 to the fourth is 81. 3 squared is 9. 5 times 3 is 15. We have this here. 2 times 81 is 162. 8 times 9 is 72. And 15 minus 7 is 8. 162 minus 72 is 90. 90 plus 8 is indeed 98. Three? Well, f of 3 is just saying we're evaluating it for when x is 3. Or really, we can say that f of 3 is equal to 98. Yeah. Now, this works in either calculator. And as you've heard, I know me and Mrs. Kendall and probably every math teacher said do not use the variables in the 30xs or the 84s because they don't work quite right. Because x in either one of these here does have a value. It has to have a value for it to evaluate it. Or to think about these here. Now we said for this here, x was what? 3, yes? 3. A button on both calculators, STO, that is store. So what we can do is we can type the number we want, hit the store key, and then hit the variable. And what that's told the calculator is from now on, whenever it sees x, its value is 3. So then I can type in 2x to the fourth minus 8x squared plus 5x minus 7. And we said this was what? 98. Three, store is right above on. And it works on either calculator. So if we look at the next one, this time we're saying x is 4. We can say 4 store x. So this is the 30xs because the variable button is just right above store. We can say negative 2x to the fourth plus 6x to the third minus 3x plus 11. Negative 129. Or we can type it in. Either one works. As we could say negative 2 parentheses 4 close parentheses to the fourth plus 6 parentheses 4 close parentheses to the third minus 3 parentheses 4 close parentheses plus 11 and get the same thing. Either way works. Questions on this here? Questions on evaluating? Now, this seems, especially with storing, seems like a little bit more harder way to type these in. But if, so the 2x to the fourth minus 8x squared plus 5x minus 7, the first one we did, if we wanted to evaluate this for when x is 3 and when x is 4, When x is 4, it's 397. Well, we also want to see when x is negative 4. Negative 2. So I could keep restoring the different number in, recall the equation, and do it a lot faster. If we're using a different equation for each number, there's not really a faster way. We feel good with evaluating. And that brings us to the last piece, in behavior. In behavior. With polynomial functions, the in behavior is what the function is going to eventually do as we increase the values of x and increase it in a positive and negative direction. I don't need the arrows over here. Because, oddly enough, no matter what type of polynomial equation we have, it's going to behave eventually in one of 4 ways. Now, the first thing we do have is the degree. The degree of the function is either going to be even, or the degree is going to be odd. There's only 2 directions it can go. It's either going to be an even function or it's going to be an odd function. It means the biggest exponent is going to be even or odd. It has to be one or the other. And the other part is the leading coefficient. Because the leading coefficient is either going to be positive or the leading coefficient is going to be negative. We only have 2 options. It's either going to be positive or it's going to be negative. And that's true if the degree is odd as well. It's only going to behave in one of these 4 ways. Now, if the degree is even, the bottom 2, and the leading coefficient's positive, they're both going to end up going up. The y values will end up increasing to positive infinity at some point. They're going to keep going up this way. Now, the reason we have the dashes in the middle is because the different types of quadratics, or not quadratics, but even degree polynomial functions, between those 2 spots will do just something different depending on the function. Let's see here, x fourth plus 2x squared plus 1. I'm trying to think of what. Okay. Trying to come up with these equations off the top of my head. You need to pass those back. Does this have batteries? Yes. Oh. Algebra. Clear. Algebra. Expand. Parentheses x squared. Oh, there we go. X to the 4th minus 13x squared plus 36. Zoom 0. Okay, not that far. Zoom 6. Negative 2 to 30. Let's go by 5s. Gosh. Negative 10, 10, 1. Negative 5, to 45. So that's, as we see here, it does make a W shape, but eventually both sides go to infinity. They go up. If the leading coefficient is negative, we can see the graph is now going down. Well, to get the same shape, plus, minus, so we have this here, and it's now going down. Now, the big thing with this is that the degree was even, and the leading coefficient was positive when it was going up, and negative when it was going down. Now, what happens in the middle can differ from function to function. But if it's even, eventually as we increase, the values of x or decrease, they'll either go up or down with a degree even. When the degree is odd, the end behavior is going to go in opposite directions. One's going to go up, the other's going to go down, depending on what it is. Now, to finish out this chart, because it is written here, that chart is included in your notes. If the degree is even and the leading coefficient is positive, f of x is going to approach positive infinity as x approaches positive infinity. And f of x approaches positive infinity as x approaches negative infinity. That's just saying as x, we increase it from the left and to the right, both are going to go up. And if the degree is even and the leading coefficient's negative, f of x is going to approach negative infinity as x approaches positive infinity. And f of x is going to approach negative infinity as x approaches negative infinity. It's going to go the same way. Odd, positive. F of x is going to approach positive infinity as x approaches positive infinity. And f of x is going to approach negative infinity as x approaches negative infinity. In odd and negative, f of x is going to approach negative infinity as x approaches positive infinity. And f of x is going to approach positive infinity as x approaches negative infinity. So I did write it here on the whiteboard. It is also included here in your note sheets. It's just not written out in a linear form, but they are all there. Okay. A lot of information there. Now let's see how this works for these problems here. Describe the end behavior of the graph of f of x equals negative 0.5x to the fourth plus 2.5x squared plus x minus 1. What's the degree? What's the degree of this here? 4. 4 is, so for end behavior, 4, it is a quartic, but this would be in even degree. Because 4 is even, so the degree is even. Leading coefficient. Negative 0.5, so the leading coefficient is negative. So, if we look at the chart, degree is even, leading coefficient's negative. So I go over here and look at that, and what it has with it is that f of x approaches negative infinity as x approaches positive infinity. And f of x approaches positive infinity as, or no, I had that right, negative infinity. As x approaches negative infinity. So since the degree is even, they're both going to be going the same direction. F of x will be going to the same spot. F of x approaches negative infinity as x approaches positive infinity. And f of x approaches negative infinity as x approaches negative infinity.
Do you care if it's like I and F for infinity? Because I can't draw the infinity. I keep drawing
Well, you can turn the paper sideways and draw an 8. Questions on this here? That's it. The green part is the answer. Yeah. So, let's look at the next one here. What is the degree of this function? 3. Since we're talking about in behavior, the degree is odd. The leading coefficient is and the leading coefficient would be negative. Because in behavior, for the degree is either going to be positive or even or odd, and the leading coefficient is positive or negative. So odd and negative, if we look over there, it tells us that f of x approaches negative infinity as x approaches positive infinity. F of x approaches positive infinity as x approaches negative infinity. And that's it. Because really, since the degree is odd, it's saying that the two ends eventually are going to go in opposite directions. And since it's negative, as we go farther to the left, it should be going up. As we go farther to the right, it should go down. Questions on this here? We do have one more. The degree is 3, which would be odd. Leading coefficient 0.25, which is positive. If we look at the chart, f of x approaches positive infinity as x approaches positive infinity, and f of x approaches negative infinity as x approaches negative infinity. And I think the biggest takeaway from in behavior is it gives us an idea of what the function should do as the values increase from the left and to the right. Because if we graph this on the graphing calculator, and it gave us something like this here, this is just a guesstimation of it. Now, it says as f of x approaches positive infinity, as x approaches positive infinity, so this side should be going up. Because if this is what the graphing calculator shows us, well, okay, yes, it is indeed increasing. But as x approaches negative infinity, as we go this direction, the function should be going down, which means somewhere to the left of the screen, it's going to cross the x-axis again. So there should be another solution somewhere out that way. Now, this is not an accurate representation of this because it has too many zeros, but this is just kind of an example of what we would be looking at. But that is nowhere near what the actual function should look like. And that's it.